Hi, hello everyone. So today we're going to have a look at, and over the next week, really, we're going to have a look at how we apply algorithms to probably the most fundamental way in Leaving Cert Computer Science, and that's the idea of search and sort. Okay, so we're going to have a look at two types of search algorithm. Okay, and then we're going to have a look at a lot of different types of sort algorithm. Okay, at least 4. Okay, now any of these can come up in the Leaving Cert, and as you know yourself, the hardest thing is first of all recognizing which one is which. But once you recognize them, how to actually, it's very easy to see these in code, but how do you actually see them in terms of their written? So how would you physically write them as opposed to code them? Because coding them can actually be quite easy, whereas actually having to rewrite it in your own words or in your own kind of visual way can be quite hard. So today we're going to have a look at a few different ones. So the first one we're going to have a look at is what's called a binary search. And it is the most simple one, sometimes called the divide and conquer method. It's been around for eons. Okay, not the actual coding of this, but the concept of it. Okay, so let's think about the logic of this one. The logic of it is to take an ordered list. This only works with an ordered list. It will not, binary search will not work and will fail if it's unordered. Okay, so in order for a binary search to work, you have to do a sorting algorithm, which obviously we're not going to be doing today, but you'd have to sort the data and then do the binary search. But it is a very efficient way of doing it. So let's think of the concept. Okay, so you find a list. Okay, let's just take the word list. Okay, and you find the middle term. So first of all, let's rearrange this. Okay, list. So ordered, it would look like this: I, L, S, and T. Okay, then you'd find the middle term. Now, this is the important thing. Okay, if you have n objects in a list, okay, and in a list, you go n plus 1 over 2 should give you the middle one. Okay, or the position of the middle one, for want of a better word. Okay, and as you notice, this is an even list, so the middle term doesn't really exist. In an odd list, 1, 2, 3, 4, 5, the middle term does exist. Okay, but in an even term it doesn't. So in order to counteract that, you go 4 plus 1 is 5 divided by 2 is 2.5, which is true. Okay, so it's halfway between them, but you round up. Okay, in this case, 1, 2, 3, 4, 5. 5 plus 1 is 6, divided by 2 is 3. No need to round up. So if it's an odd list, you're obviously just going to round up to the nearest one. So in this case, it'll zero in on a S as its middle term. It's not the middle term, but it has to round in on something. And by convention, it's easier to round in on this one. Okay, so that's the first thing. So let's think about it. So that's step 1 in our algorithm. Okay, find the middle term. Step 2, if the middle term is the one you want, stop. So if I'm looking for the S, stop, because I found it. If I'm looking for the tree, stop, I found it. Now, step 3, if it's not, compare what you want to the middle. This is the important bit. Okay, so if it's not S, compare what I want. Let's say I want I. If that's not I, then I'd compare it to it. And this is the very important. If what I want is before the middle, remove the upper half. Aha. So, what are we saying? So, I'm looking for I. So I reorder the list. Okay, I find the middle point. It's an odd number, so the middle point is going to be the third character in this case. Okay, so the first thing I do is found the middle term. It's S. If the middle term is I, I've stopped. It's not I. If it's not I, then compare I to S. If I is before S in the alphabet, yes it is, I ignore everything from S up. See that? So I get rid of him and I get rid of the T. Then I'm just left with IL. Okay. Obviously, if it was after it, I'd just ignore, if it was after it, I'd just ignore the rest. And you get the idea. So you either move the left or the right. So what am I left with? I'm left with half, haven't I? Half the list. Binary. So I've broken it in half. Okay. And then I'm going to repeat steps. Step 4, repeat steps 1 to 3 until you find whatever. Okay, so go back to step 1, find the middle term. I have an even number, so that's 2 of them left. 2 plus 1 is 3, it's halfway. Okay, so I'm going to land on L as being my middle one. Okay, is L I? No. Is I less than or greater than I? It's less than, remove I. Step 1, find middle term. There's only one thing left. 1 plus 1 is 2, divided by 2 is 1. So there we are. If middle term is the one you want, stop. Yes, it is. Okay, simple as that. I'll try it again just to show you. Okay, so pay close attention, as the man says. Right, so pay very close attention. I'm going to use, I'm trying to think, I'll just use numbers this time, it's easier. Okay, so let's say I have 4, 3, 7, 2. I'll go with odd or even. I'll go with odd this time. It might make it a bit easier. Okay, 4, 3, 7, 2, 1, 8, and 9. Okay, so I want to find 2. Find 2. So step 1, order them. Okay, so let's put them in order. 1, 2, 3, 4, 7, 8, 9. Step 2. Step 2, find the middle. Okay, so n plus 1 over 2 will give me the middle. N is 1, 2, 3, 4, 5, 6, 7. 7 plus 1 is 8. Divided by 2 is 4. Use different color. There's the middle. Okay. Step 3. Check if middle is 2. Step 4. I'm just going to write all the steps here. If not, check if 2 greater than or less than middle. If greater than the middle, remove left side. If less than, remove right side. Step 5, repeat step 2 to 4. Okay, or repeat step 2 to 5 really, because I'm going to keep doing this until at least hits there. So let's follow it through. Find the middle. Done that. Check if the middle is 2. No, it's not. If not, check if 2 is greater than or less than middle. 2 is less than the middle. If it's less than the middle, remove the right-hand side. So I'm going to remove the right-hand side. So now I'm left with 1, 2, and 3. Okay, repeat steps 2. Step 2, find the middle. The middle here is 2. Okay, check if middle is 2. Yes, it is. Yay! But let's say if it wasn't, then I'd either remove the right-hand side or remove the left-hand side and recheck it again. Okay, so see how quickly that's done. But the key to this is it has to be ordered. If it's not ordered, it won't work. Okay, it won't work. Now it's very easy, and we will see this maybe next week when I'm going to do all these algorithms in code Python form, but for our Python class. But what you will see is it's pretty easy to spot once you know what it's meant to be doing. In other words, it's a divide and conquer. So at each iteration of the loop, it's dividing it by 2, finding the middle, and then ignoring greater than or less than. So it's actually easy to spot in a code, in a Python code, what it's meant to be doing. It's a pretty easy one to actually spot. Okay, so that is a search algorithm, binary search algorithm. It's like it's everyone's favorite, I think everyone would say, but you know, it is what it is. So on to our second one. Our second search algorithm is a linear search. Okay, and the advantage of this over a binary search, it can be used on unordered lists. Okay, it's the most bluntest one in the universe, literally. It's the one that, you know, it's the one everyone probably learns as a kid, even though you're not learning it. Okay, so what do we do in an unordered list? Okay, you pick what you want. So let's say you have your search parameter. I'm looking for a 4. Okay, you look at the first item. Step 2, if first item is target, stop. Step 3, if not, look at next. Step 4, repeat steps 2 to 3 until you find target or you reach the end of the list, because sometimes the target isn't in the list. Okay, it's much simpler, you can see that, but it's definitely not as efficient. Okay, it can be used in any type of list. It doesn't have to be ordered. It tends to be only used on small lists though. Okay, for that reason, because the bigger the list, having to go through every one of them. Okay, the minute you've got an ordered list, a binary search is way more efficient than a linear search. Okay, it takes way fewer steps the bigger the list. If we only have a tiny list, let's say if we have 10 things in a list, then using a linear search or a binary search makes no difference. But if you had 10 billion things in a list, then using a linear search is way less efficient. Okay, so let's have a look at the list. Okay, let's do 7, 21, 52, 68, 92, 99. And I want to target, I want to find 68. Okay, so let's see how many steps it would take us to find 68. So it would look at the first item. Is 7 equal to 68? No. Look at the next one. Is 21 equal to 68? No. Okay, let's look at the next one. Is 68. Is 52 equal to 68? No. Is 68 equal to 68? Yes. So it took me 4 lines of searching to find it. That'll be 4 iterations of the code. Okay? If we were doing binary, I've put these in order. So in binary, we have 1, 2, 3, 4, 5, 6. We have 6 things. So what would the binary do? The first thing it would do, it would n plus 1 over 2. So it's that 7 over 2, it's 3.5, and move it on. That would be the middle point. So what's the first thing in a binary code? If the middle number is the number, stop. So straight away in binary, you've got it. But let's say I was looking for 92. Okay, so let's say it lands on 68 as the middle number. Okay, is 68 not the one I want? Is 68 equal to 92? No. So what would binary do? Okay, it would check. So this is all happening in the one iteration. It would check that 92 was either greater than or less than 68. Okay, so obviously it's greater than, so it would ignore all them, and then it would start again, wouldn't it, with just 92 and 99. So what would it zero in on? It would zero in on 99 because it's n plus 1 over 2 and round up. So it would check with it 99. No. So is 99 equal to 92? No. And then by the third iteration, it'll then be left with 92. Yes. And that's only when they've only got 1, 2, 3, 4, 5. Only when you've got 6 things, you can already see it's gotten a bit better. Imagine with 6 billion things, how quickly. Imagine if you had 6 billion things and this, the one you were looking for was this 599,000 millionth, 999,999,990th element or object in that list. You'd have to go through all the other ones to get that last yes. You wouldn't have to go through all of them because it would divide down and you'd probably get it in less than 30 lines of searches. So that's the brilliance of it. Okay, so there's a linear search. So you can see the advantage of one over the other. Okay, thank you, lads. Goodbye.